Imagine a particle so elusive that it can pass through light years of lead without a trace. This particle is so incredibly small and interacts so weakly with matter that it can travel through entire planets, stars, and even galaxies without being stopped or deflected. It's as if it exists in a parallel dimension barely touching the universe we know. A particle that outnumbers all the atoms in the universe. These particles are everywhere, streaming through us by the trillions every second, yet we remain completely unaware of their presence. They are the silent witnesses to the universe's most dramatic events, from the birth of stars to the cataclysmic explosions of supernovae, a particle that holds the secrets to the most energetic events in the cosmos. When a star explodes in a supernova, it releases a flood of these particles, carrying with them information about the processes that occur deep within the star's core. Similarly, when black holes devour matter, or when gamma-ray bursts light up the sky, these particles are there, providing clues to the extreme physics at play. This is the neutrino, the universe's ghost particle. Neutrinos are incredibly difficult to detect because they rarely interact with other matter. They pass through space and matter almost as if they were ghosts, leaving behind only the faintest traces of their existence. Neutrinos are fundamental particles, meaning they are not made up of smaller constituents. They are one of the building blocks of the universe, essential to our understanding of the fundamental forces and particles that make up everything around us. They are a key part of the standard model of particle physics, our best understanding of the fundamental building blocks of matter and the forces that govern them. The standard model describes how particles like neutrinos interact with each other and with the fundamental forces of nature, such as electromagnetism and the strong and weak nuclear forces. The standard model, however, doesn't tell us everything about neutrinos. There are still many mysteries surrounding these particles, such as their exact masses and the way they oscillate between different types or flavors as they travel through space. There's much more to learn about these enigmatic particles. Scientists around the world are working tirelessly to unlock the secrets of neutrinos, using advanced detectors and experiments to catch these elusive particles and study their properties. The study of neutrinos offers a unique window into the universe's most extreme environments, from the heart of the sun to the remnants of exploded stars. By observing neutrinos, we can gain insights into the processes that power these celestial objects and the extreme conditions that exist within them. By studying neutrinos, we can learn about the processes that drive these celestial objects. Neutrinos produced in the core of the Sun, for example, can tell us about the nuclear reactions that fuel our star and provide the energy that sustains life on Earth. We can also gain insights into the fundamental laws of physics. Neutrinos challenge our understanding of the universe, pushing the boundaries of what we know and opening up new possibilities for discovery. As we continue to study these ghostly particles, we move closer to uncovering the true nature of the cosmos and the forces that shape it. Neutrinos are incredibly difficult to detect. This is because they interact with matter extremely weakly. They are like tiny, chargeless ghosts that effortlessly pass through planets, stars, and even our own bodies. Trillions of neutrinos from the Sun pass through you every second, yet you never notice them. Their weak interaction is what makes neutrinos so fascinating and challenging to study. To catch these ghostly particles, we need ingenious detection methods. We also need massive detectors, often built deep underground, to shield them from cosmic rays and other interfering particles. Despite their elusive nature, the very weakness of neutrino interactions makes them valuable messengers. They travel across vast cosmic distances unimpeded. They arrive on Earth carrying pristine information about their sources. Neutrinos come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. These elusive particles are incredibly small and almost massless, making them one of the most mysterious components of the subatomic world. Despite their tiny size, neutrinos play a crucial role in the universe, participating in nuclear reactions and helping to drive the processes that power stars, including our own Sun. Each flavor is associated with a charged lepton, the electron, muon, and tau particles. These leptons are fundamental particles themselves, and their interactions with neutrinos are key to understanding the behavior of matter at the smallest scales. For instance, when a neutrino interacts with an electron, it is specifically an electron neutrino that is involved in the process. For example, electron neutrinos are produced in nuclear reactions that also produce electrons. These reactions occur in environments such as the core of the Sun, where nuclear fusion takes place, and in nuclear reactors on Earth. The study of these neutrinos helps scientists understand the fundamental forces that govern particle interactions. These three flavors are not fixed, however. Neutrinos have the remarkable ability to change from one flavor to another as they travel. This transformation is known as neutrino oscillation, and it is one of the most intriguing phenomena in particle physics. The discovery of neutrino oscillations challenged our understanding of the standard model of particle physics. This means that a neutrino that starts out as an electron neutrino can transform into a muon neutrino or a tau neutrino over time. This oscillation is influenced by the neutrino's energy and the distance it travels, making it a complex and fascinating subject of study. This oscillation is a quantum mechanical effect, a testament to the strangeness of the quantum world. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, provides the framework for understanding neutrino oscillations. The phenomenon highlights the probabilistic nature of quantum mechanics, where particles can exist in multiple states simultaneously and change states unpredictably. The discovery of neutrino oscillations was a major breakthrough in particle physics. It provided the first direct evidence that neutrinos have mass, albeit a very tiny one. This discovery was so significant that it earned the scientists involved the Nobel Prize in Physics. It opened up new questions about the nature of neutrinos and their role in the universe. It implied that neutrinos have a very tiny mass, a property that was not predicted by the original Standard Model. The Standard Model, which describes the fundamental particles and forces in the universe, had to be revised to accommodate this new information. This has led to ongoing research and experiments aimed at measuring the exact mass of neutrinos and understanding their properties in greater detail. This discovery opened up new avenues of research into the fundamental nature of neutrinos and their role in the universe. Scientists are now exploring how neutrinos might influence the evolution of the cosmos, the behavior of supernovae, and the formation of elements. The study of neutrinos continues to be a vibrant and exciting field, promising to reveal more about the hidden workings of the universe. Neutrino oscillations are a mind-bending phenomenon. Imagine a particle changing its identity as it travels, kind of like a chameleon changing its color. An electron neutrino emitted from the Sun might transform into a muon neutrino or a tau neutrino by the time it reaches Earth. The probability of these oscillations depends on several factors, including the neutrino's energy and the distance it travels. By studying the patterns of these oscillations, scientists can learn about the differences in mass between the three neutrino flavors. Neutrino oscillations have profound implications for our understanding of the universe. They suggest that neutrinos might play a role in the matter-antimatter asymmetry, one of the biggest mysteries in cosmology. Furthermore, understanding neutrino masses could lead to new physics beyond the Standard Model. Neutrinos are produced in a wide range of cosmic events, from the nuclear fusion that powers the Sun. These tiny, nearly massless particles are born in the heart of stars, where intense heat and pressure fuse hydrogen atoms into helium, releasing energy in the form of light and neutrinos. The Sun, our closest star, is a constant source of neutrinos, streaming out into space and passing through everything in their path, including Earth and all its inhabitants. But the Sun is just one of many sources of neutrinos in the universe. These particles are also produced in the violent deaths of massive stars in supernova explosions. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support its own weight. The core collapses and the outer layers are blasted into space in a spectacular explosion known as a supernova. Neutrinos are not just products of stellar processes, they are also relics of the Big Bang, the universe's fiery birth. In the first few seconds after the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, neutrinos decoupled from the rest of the matter and began to travel freely through space. These primordial neutrinos still exist today, providing a unique window into the conditions of the early universe. Supernovae are particularly prolific neutrino factories. The study of these neutrinos can reveal much about the processes occurring in the heart of a dying star. In the final moments of a massive star's life, its core collapses under its own gravity, releasing a tremendous burst of neutrinos. This collapse happens in a fraction of a second, creating a shockwave that propagates outward, blowing off the star's outer layers. The energy released in this event is so immense that it can outshine an entire galaxy for a brief period. These neutrinos carry away a significant portion of the supernova's energy, far exceeding the visible light emitted. The neutrino burst is so powerful that it can be detected by observatories on Earth, even from stars located millions of light-years away. By capturing and analyzing these neutrinos, scientists can gain valuable insights into the mechanisms driving these cataclysmic explosions. By studying neutrinos from supernovae, we can gain insights into the processes that drive these cataclysmic events. Neutrino observatories, such as the Super-Kamiokande in Japan and the IceCube Neutrino Observatory in Antarctica, are designed to detect these elusive particles. These facilities use large volumes of water or ice to capture the faint flashes of light produced when neutrinos interact with matter. We can also learn about the properties of neutrinos themselves, such as their masses and how they interact with matter under extreme conditions. Understanding neutrinos is crucial for particle physics and cosmology, as they play a key role in the evolution of the universe. By unlocking the secrets of these ghostly particles, we can gain a deeper understanding of the cosmos and our place within it. If you found this information useful, do like, subscribe and comment on this video to support our channel and stay updated with our latest content.